find the ones you had sent out before.
Okay, I'll double check. I mean, yeah, I normally receive it. I just hadn't gotten it this week, so
you should have,
email it.
Oh,
yeah, you
what's the
should
problem?
have received it. But sometimes, okay, I know I grade my other classes' homework, and sometimes the attachments don't come through, or sometimes every now and then the email doesn't go through. So, well, check on it, okay?
I will. Thank you.
Okay, my clock says 8 o'clock. Let's see. We're going to spend today reviewing because we have tests tomorrow. The test will cover October 16th, October 22nd or 23rd. Yeah, same one. October 30th homeworks. And I posted a practice exam on Tuesday. So I hope you've looked at that. I must be able to see you on camera, okay? If I can't see you, I won't grade your exam, and I'll arrange for you to take the exam later on campus. What else? Yeah, I want you to show me that you understand, okay? Let me show you what I mean. And Mr. Miller sent out a little handout about this kind of thing too. In this context where I don't know where you're getting your information, a lot of you just pull stuff off the internet, okay? I want to see if you're doing that, I want to see you understand what you got. Understanding is everything. I'm going to share my screen. And let's see. Well, that's it. Okay. Oh, there we go. All right. Yeah. Here's something I noticed on your last exam. It is kind of an example of what I'm talking about. Suppose I ask you to find the derivative of some function. Let's see. Let me make up a function. So the problem says find the derivative, okay? And what I see in your paper is x to the 4th plus 3x plus 2 is equal to 4x cubed plus 3. That's not true. This is the function. This is the derivative of the function. The function and its derivative are related, but they are not equal. So this is a mathematical statement. It says this function is the same as its derivative. That is not generally true, and it's certainly not true in this specific example. So don't write things like that. I also don't like it when I see things like, okay, you write down this, and then you write down this, and then you write down 4 or something. Okay. There's no sentence there. I don't know what x to the 4th plus 3x plus 2 is. You didn't say what 4x cubed plus 3 is. You didn't say what 4 means. So use sentences, mathematical sentences, sometimes English sentences, to explain to me what you are doing and what your work leads you to conclude. A lot of you are doing better with that, okay, but we still need to improve. Okay, so yeah, I am looking to see if you understand the material. Okay, so enough on that. Before we get started with the review, is there any problem somebody would especially like me to look at?
I don't have a suggestion, but you're not screen sharing right now.
I'm not, oh,
No, ma'am.
I'm not, my screen's not showing?
No, ma'am.
Okay, let me go back. The screen sharing ended unexpectedly. Okay. All right, well, that explains that. Let me see. Okay, it says I may need to reboot. Let me see if I can share the screen now. Okay, looks like it's all right. Okay, can you see my screen now?
It just cut out for some reason.
Okay, that means I need to reboot. All right, so I'm gonna reboot. You all just stay where you are. It'll take me a few minutes, okay?
Yes, ma'am.
Okay, I think I'm back. Okay, can you see my screen now?
Yes, ma'am.
Oh gosh, are you still there?
Yes, ma'am.
Okay, great. Okay, let's see. What's this? Notes is not coming up.
Try double tapping the home button and then slide up on notes. It'll close out, and then once you go back in, it should fix that problem.
The home button.
If I'm not wrong, there should be a button at the bottom of the screen, kind of by where you would plug the power cord in.
The power cord in. Okay. This one. Okay. Oh, great.
Either
Okay.
that or if I do recall, you can just slide up from the bottom of the screen to get that option.
How about that? All right, thank you. Okay. All right, but it's not working. That's the only problem. Oh, yeah, now it is. Now it is. Okay. Okay, thank you, Mr. Levy. Okay, maybe we're back to where we were. Now, would anybody like to request that I go over any homework problem or any practice exam problem or any special topic?
Could you go over number 3
Number 3.
in the review?
Okay. All right. That's the one we were doing yesterday, right? You mean
It was similar.
number 3. Yeah. It was very similar. Yeah, let's do that one. Okay. Show that the function, this is on the practice exam. Okay, my pen's not writing. Just a minute. Not writing. I want to duck it for a minute. Now it's writing. All right. Okay. Number 3. Okay. I hope we're back in business. We want to show that the function f of x equal to x to the 5th plus x cubed plus x plus 1 has exactly one real root. Okay, so to do this, you must show actually 2 things: that the function has at least one root, but it doesn't have 2. So how are we going to do that? Well, so I'm going to do the first thing, show that f of x has at least one root. And for that, we use the intermediate value theorem. Okay, which we talked about yesterday. And we want to, showing that it has at least one root. So we must show that f of x equal to 0 has a solution. Oops. Okay. What's all that stuff? Okay, that's. Yeah, and for us, the only solutions are real solutions, not complex ones. We're not dealing with complex numbers in this course. Okay, well, if I can find, so some number C1 such that f of C1 is greater than 0, and another number C2 such that f of C2 is less than 0, then we can use the intermediate value theorem to conclude there must be a number such that f of C is equal. All right, well, let's just shop around. F of 0 would be 0 plus 0 plus 0 plus 1, and that's positive. Okay, so I found a number like that. Okay, I think if I put in -1 for x, that value, f of -1 is going to be negative. F of -1 would be -1 minus 1 minus 1 plus 1 is -2 is less than 0. Okay. So, intermediate value theorem says that since, let's see, -2 is less than 0 is less than 1, there must be some number C little c actually in the interval from -1 to 0. Okay, that's based on those two numbers, such that f of C is 0. Okay, so the intermediate value theorem shows that you must have at least one real root. Okay, so by the intermediate value theorem, f of x has at least one real root, and we actually know that there is a root between -1 and 0. But okay, we want to prove that f doesn't have any more roots. So part B, show that there are no other roots. Okay, and there are a couple of ways you could do this. One is just to take the derivative. So one way. F prime of x is equal to, okay, 5x to the fourth plus 3x squared. Right on the next line. 5x to the fourth plus 3x squared plus 1. And that function, okay, 5x squared, 5x to the fourth, that's always non-negative. 3x squared is always non-negative because of, okay, of the x squared, and previously because of the x to the fourth. So this has to in fact be greater than or equal to 1. Okay, that's the smallest thing that the derivative could be. And that means that f is an increasing function over all the reals. Right? Because you took a derivative, there are no critical numbers. You've got a plus, the function's increasing. And an increasing function, well, it can't cross the x-axis twice. Okay, we know we have, call that -1, call that 0. There's some number in there where that function is 0, but it's increasing over all of the reals. It cannot come back and go through 0 again because it would have to have a critical number in particular, and a local maximum. Okay, so that's one way. Another way is, okay, and this is really even more fundamental. Use the mean value theorem. And that says, let's see, that, okay, you have f, actually f is continuous and differentiable, this function, over all of R. Okay, remember you need, well, for the mean value theorem, you need this to be true on a closed interval, and that the differentiability needs to be hold on the open interval. So the mean value theorem requires f continuous on AB, f differentiable on the open interval AB. Okay, and the conclusion that you get, if this is true, okay, these two things are true, then there is some number C in AB such that f prime of C is f of B minus f. No, my writing's not so good there. F of B minus f of A over B minus A. So how am I going to use this here? Well, I want to prove that this, let's call this root, okay, we're going to call, yeah, so we've already identified one root, one number between -1 and 0. Okay, so suppose to the contrary, that there is another root. Which I'll call, what should I call it? I'll call it D. Okay. So we have, so C is not equal to D, and F of C equals to F of D equals to 0. Well, then I'm going to look at the interval CD. Okay. And actually, I don't know whether C is less than D or D is less than C. Either one could happen. So if C is less than D, then C to D is a closed interval. We've got the function polynomials continuous on everything. So in particular, it's continuous on CD and on the open interval, a differentiable on the open interval from C to D. So the mean value theorem
Did you say that if C is less than D, then CD is a closed interval?
Yeah, right. If it, so it could happen that, okay, so we know that there is some root in here, but maybe is the other root over here? Now, we already know that the function is increasing, so there is no such D, but okay, this is a whole nother approach to, another approach to showing that there's only one real root. Okay, so suppose that C is less than D. I'll argue that first. Then the mean value theorem says there is some, okay, I can't call it C because C already means something. There's some number, I'll call it S, in the interval CD such that F prime of S is F of D minus F of C over D minus C. And that says, well, F of D is equal to F of C. That says that F prime of S is equal to 0. But no such S exists because F prime of X is, what was it, 3x to the 4th plus 5x to the 4th plus 3x squared plus 1. Which is greater than or equal to 1 for all x. Okay, so this is what you call a contradiction. I got that F prime of S has to be 0, but F prime of X is always greater than or equal to 1. Both of those things cannot be true. This is a contradiction. So no such S exists. And there is no other root D. Okay. Well, that was assuming C is less than D. If you assume D is less than C, then the interval is from D to C. But okay, you get the same argument. And you get the same contradiction. Okay, so that was probably the easiest thing is to show that, take that derivative, see that it's greater than equal to 1 for all x, and that means the function is twice. It can't come back. Okay, does that help, Daniel?
Yep. Yes,
Okay,
ma'am.
good.
Thank you.
You're welcome. Okay, well, let's see. How about we look at the graphing problem? You will have one of these.
That's number
Okay.
5.
Yeah. Unless somebody really wants me to do something else. Yeah, those graphing problems, but well, notice that it counts 20 points on this exam. It'll count at least that much on yours, okay? Maybe even more, because they are long and involved. Okay, so we have, this is number 5 on the practice exam. We have y is 2 times the square root of x minus x. Domain then. Okay. Well, what's not in the domain?
Any negative value of x?
Yes. So only x greater than 0. So yes, any negative numbers would give you that square root not existing. So the domain, all x greater than or equal to 0. So that means that when I start graphing the function, I'm not going to see anything to the left of the y-axis because there are no x's over here. Okay, why don't I put on some lines and grids so maybe it'll do a nicer job. Yeah, the thing's going to be all to the right of the y-axis, the domain. All right, so that was part A. Bader, okay. He's in my other class. He doesn't need to be let in. Okay, intercepts. Well, the y-intercept's pretty easy. Y at 0 is 0. So that's your y-intercept. And in fact, it's also an x-intercept. Yeah. So y-intercept because y at 0 is 0. It's an x-intercept because when you put a 0 into y, it's 0. X-intercepts, well, x equal to 0. And
X equals to 4 as well.
okay, yeah. So, okay, thank you. Let's work that out. That's probably right. Yeah, let's see. So that would say you don't want to miss any roots. Okay. So x squared is 4 times x. That says x squared minus 4x is 0, is x times x minus 4. Yes, you are correct. X equal to 4 is another intercept. Okay. Okay, so what do we know so far? We know, I'm going to go ahead and start graphing. Well, okay, I'm going to let Bader in. Oh, he's trying to get in because they're having a test. I'm not sure, that would just confuse him. Okay. Yeah. All right. So 0 and 1, 2, 3, 4. Those are points on the graph right there. Okay. So let's see. What about asymptotes? I don't think you'll have any vertical. Well, the only place, well, this function is not defined on the entire real line. It stops at 0. But the function is continuous at 0. It is continuous everywhere else. Sometimes at the edge of a domain, you'll have a vertical asymptote, but not when the function is continuous at that point. Okay, so no vertical asymptotes. Y is continuous, okay. Well, what about horizontal? So there's none of that. Horizontal.
There won't be any horizontal either because the minus x causes the function to spiral downwards.
Okay, that's right. And yeah, let's see. I'm having trouble spelling here. Okay, there. Yeah. Okay. So, well, to look for horizontal, you have to look at two limits, correct? The limit as x goes to 0, x goes to infinity of the function. And that's equal to, yeah, the square root of x is going to be in magnitude smaller than x. And that, let me just do this, okay, to make it absolutely clear. I'm going to factor a square root of x out of that 2 times the square root of x. This is, I can factor it like that, right? Because square root of x times square root of x is x. Well, the limit as x goes to infinity of the square root of x is plus infinity. And the limit as x goes to infinity of 2 minus the square root of x, that's minus infinity. A large negative number times a large positive number is a large negative number. So this limit is minus infinity. Okay, and that's what Mr. Levy was saying. So there's not one in the positive direction. Can I even look at this?
No, ma'am, because as we said before, it doesn't reach towards negative infinity.
That's right. The x can't be less than 0. So it can't take on large negative values. No. X is not defined. Y is not defined. Okay. Y is not defined for x less than 0. So it's not possible to have one in the negative direction. Okay, so that, no asymptotes. And finally, let's see. We are ready for the derivative information. So that's the D and E. Those intervals of increase and decrease, and the local minima and maxima. And so we need y prime, which would be, okay, the derivative of 2 times the square root of x minus x, which is the derivative of 2 times x to the 1/2 minus x, which would be equal to 2 times 1/2 x to the minus 1/2 minus 1. And that would be 1 over the square root of x minus 1. And okay, it's better to have it written as a product. Well, I'm going to, product and a quotient are basically the same thing, okay. Get a common denominator of the square root of x. So that would give me 1 minus the square root of x over the square root of x. And that's equal to y prime. I've got it written in a nice form that I can deal with. Okay. So, question is, what are the critical numbers? Oh, stop it. And certainly x equal to 1 is 1, correct? Because 1 minus the square root of x is 0 when x is equal to 1. And then that's the only place that numerator is 0. And the square root of 1 is not 0. So the one critical number is 1. I guess there's also, if x is 0, then f at 0 is defined, but f prime at 0 does not exist. Okay, remember you get critical numbers that way too. It's an endpoint, 0 is an endpoint, so I don't think we're going to get any changes here. But let's see what happens. Okay, so we've got two critical numbers, 1 and 0. Here's my number line. And this is y prime information. Put 0 there. Remember, nothing over there is in the domain even. Put 1 there. Okay, so what does the derivative do between 0 and 1? And there's the derivative. Take a fourth. 1/4 is in that interval. And I picked that because it's easy to take the square root of 1/4. Okay, so I'm looking at
Could
1.
you scroll up? We can barely see your number line.
Okay, like that?
No, the other way.
The other way.
Yeah, there you go.
Okay. Okay, so I can use 1/4 to check that interval. And it helps us see. Remember, write the derivative down. 1 minus the square root of x over the square root of x. Okay, well, the square root of the denominator is always positive, right? Well, except at 0. But 0 is not a number we can check. Square root of 1/4 is 1/2. That's positive. 1 minus the square root of 1/4 would be 1 minus 1/2. That's positive. Okay, positive, positive. And that means the function increases. Okay, well, number greater than 4, how about 4? Easy to take the square root of 4. And that would give, okay, square root of 4 is 2 in the bottom. 1 minus the square root of 4 is 1 minus 2 is negative. So decreases. Okay, so we got information. F increases on the interval 0 to 1, and F decreases the rest of the time. Whoops, you don't ever put infinity in there as an endpoint because infinity is not a number. There, okay. And f of 1 is, okay, well, what is it? F of 1, go back to your
It
phone.
would be the absolute maximum.
Right. And that's 2 times the square root of 1 minus 1, which is 1. Yes, and that is both a local maximum and an absolute maximum because, yeah, the thing goes up and then it comes down. It can't get any higher than that 1. Okay, and that's our first derivative information.
And also, for 0, comma 0 would be a local minimum.
Uh, True. Okay. Or I guess technically how you would call it. But yeah, f of 0 is a local minimum. Yes. Okay. So let's put that information on our graph, which we have already started. And maybe I'll color it blue. I know that, okay, that was 4, right? And f of 1 is 1. F of 0 is 0. We go up. Oops, it doesn't go beyond the y-axis there. We go up, we come down. And with that, not that many wiggles, I'm sure. But okay, that's what we have so far. And the only thing left is to check concavity and for points of inflection. Let's see, so let's do that. So finally, this would be parts F and G. Okay, concavity, points of inflection. That's what parts F and G are asking about. And for that, we need the second derivative. So we need y double prime. And that means I need to remember what y prime is equal to. Okay, so let me use that form to get the second derivative because that's a difference of two functions and it's easier to use as far as getting the derivative. 1 over the square root of x. Let's see. Okay. And that says that y double prime, and okay. I still would like to write it in a nicer way. That's x to the minus 1/2 minus 1. And that makes it easy. That's minus 1/2 x to the minus 3/2. Okay, so that's y double prime. Well, there's a place where y double prime's not defined. So technically that's a critical point, but it's an endpoint of the domain too. So concavity is not going to change there, okay, because there is nothing to the left of 0. It's not defined as 0, and it's never 0, right? It can't be 0 because the numerator here is minus 1. Minus 1 is not ever equal to 0. So there are no critical points. Well, there's 0. 0 is the only critical point for the second derivative. But it's not where a change occurs because it's at the end. So what you got, now this is for y double prime. 0's the only critical point, and there's only one interval to check, right? The interval from 0 to infinity. Well, if I put in, say, x equal to 1, that's going to be minus 1/2 for the second derivative. So it's negative, and that means it's concave down on its entire domain. So y y is concave down on the, okay, on the entire domain, and there are no points of inflection. Because it's always concave down. It doesn't change from down to up or from up to down. It's just down, period. So let's go back to our graph. We pretty much got it right, I think. That looks like it's concave down. Okay. Okay, over the whole thing. And okay, this never becomes a straight line. It kind of looks like it in my picture, but it's probably gets pretty close to being a straight line as you take x to infinity. But there it is. And we investigated everything. Any questions? Horizontal though. Okay. You will have one of these tomorrow. Okay, so we're at 8:50. Maybe
How long
we'll
will
have,
we have on the test?
huh?
How long will we have on the test?
Okay, I will start it at shortly after 7:30. Okay, so you can start early. And then,
How
well,
many questions will be on the test?
about the same numbers on the practice
Because
exam.
this is
Okay, this doesn't tell you very much,
yeah.
Mr. Gray. I could put 15 questions on there, and if they're very short, it wouldn't be very long. Or I could put just one question on there, and if it's really hard and long, it could take the whole hour. It's about the same as the practice exam, okay?
All right.
Okay.
All right. The reason this is a very complex and long problem. And I wanted to. I haven't actually looked at the practice test. I've been studying my homeworks.
That's good. Look at the practice test, work it out. This one was not too bad. Okay. Not too many snags. It wasn't difficult to take the derivatives, so it was pretty easy to get the information fairly fast. Now, I was explaining everything and going over everything, so you won't be doing that when you're taking the test. And yeah, I'm not going to put anything that's terrible. I choose problems carefully. I choose them so they are doable in the allotted time. Okay. And
I understand that.
okay.
That I really do. I just wanted to make sure I knew what was going on before I went ahead, because I am a rather slow writer myself.
Okay, we'll get started as soon as I post the test at 7:30 or so. You'll have longer time to work it. Okay. Well, I do tomorrow. Let's see. I have a class after yours, so I will not be able to let you stay much after 8:55.
Will we be allowed to use notes?
Yes, you can use your notes. Same rules as usual. You can use your notes. You cannot use your electronic devices not to help you work the problems. I must be able to see you on camera the entire time. Okay, so I will see you guys tomorrow morning. Okay. If you want to stick around and ask something quickly, you can do so, although I've got to go pretty fast because my other classes have been in exam this morning. So you can go. You too.
Bye.
Dr. Kennedy?
Bye.